conference. The first speaker is Chris Vale, and he will talk about 2D and 3D Fermi gases. Please.
Thanks, Ivy. And so I'd like to begin with by thanking the organisers for the invitation to come to this beautiful location. It's really a pleasure to be here and have such wonderful scenery, and also for stimulating such a conference like this to promote interaction between the two communities. I think it's a really nice idea, and I'm happy to be part of it. So today I'm going to talk a little bit about some experiments that we do at Swinburne looking at ultra-cold Fermi gases. We're located, I've possibly had to travel further than anyone else here to be at this conference. So on Andrea's map yesterday I was the dot that was possibly furthest away from Camarino. But we also have some nice things in Melbourne as well. So you can find good coffee in Melbourne, and we have some nice coastline there as well. So I like to show that. Okay, so a brief overview of what I'll talk about today. Firstly, I'll give a very kind of gentle introduction to the field of ultra-cold Fermi gases and what they are and what we can do with them. And then I'll describe how one of the techniques we've used at Swinburne to make measurements or to characterise these systems based on Bragg spectroscopy, which is just an inelastic scattering type experiment. Then I'll talk about some more recent work looking at, or by using Bragg spectroscopy to probe the gas locally, so making spatially resolved measurements, and how we use that to see an in situ signature for air condensation in a Fermi gas. Then I'll spend a little bit of the last bit of the talk talking about our latest work, which is looking at two-dimensional Fermi gases, so particularly the crossover from 2 to quasi-2D to 3 dimensions, and some preliminary measurements that we've made of the equation of state of these Fermi gases in 2 dimensions. All right, so let's start with 3D Fermi gases though. So the system, when I talk about ultra-cold Fermi gases in this talk, this is what I mean. So basically we have a balanced mixture, a spin-balanced mixture of spin-up, spin-down fermionic atoms. We use lithium-6. And we have this nice trick with ultra-cold Fermi gases, or with some particular ultra-cold Fermi gases, that we can essentially tune the S-wave interactions between the spin-up, spin-down particles. So just to put things in perspective a little bit, these atoms interact via the van der Waals potential, which is actually just a very short range potential. And typically at the energy scales we're interested in, the de Broglie wavelength of the colliding particles is much, much longer than the size of this potential. So it's always S-wave scattering that we're interested in, or generally S-wave scattering that we're interested in here. And we can parameterize the collisions by this scattering length A, the S-wave scattering length, and using this Feshbach resonance we can tune this value of A to become large on the scale of the mean interparticle separation. So we can access what's a very strongly correlated regime by tuning the interactions here. And I'll talk a little bit more about that on the next slide. But just to put things in perspective, when we perform our experiments, so we use laser and evaporative cooling techniques to cool this gas down to temperatures something like 0.1 of the Fermi temperature. So Fermi temperatures in our system are typically something like 500 nanokelvin or a few hundred nanokelvin. So we get down to the kind of tens of nanokelvin temperatures. And we have something like 200,000 atoms per spin state. So it's a fairly small sample by comparison to what we've seen in yesterday's talks, but nonetheless we can still probe it and learn interesting things from it. So I'll just talk a little bit now about Feshbach resonances, because this is really a tool that's become very powerful in cold atom physics. But I'm going to give you a grossly simplified picture. And so rather than drawing van der Waals potentials and multiple coupled channels, I'll just show you a very simple picture that captures the essential physics of essentially what happens when we tune across the Feshbach resonance. So basically we think of the collision of two particles in the centre of mass frame, where we've got a relative coordinate and a centre of mass coordinate, and we're just looking at the relative wave function. And so because it's S-wave scattering, the size of the potential is very small, so it's all isotropic scattering. So we can think of it, we can approximate the situation just as a simple finite square well in 3 dimensions. And so depending on the depth of the finite square well, you get a range of different solutions for the scattered wave function. So if you've got a fairly shallow square well in 3 dimensions, it has to be larger than a certain depth before you can support a 2-body bound state. So if you've got a fairly shallow square well, then you just get this, the wave function turns over a little bit more rapidly in this deep region, and then it goes off and oscillates very slowly. So this is essentially the wave function out here where the potential 0 is linear, because it's such a long wavelength sine wave. Then you can get to this interesting point where if you increase the depth of the potential a little bit more, then you start to, you just introduce a bound state into the potential. And so here you've got a 0 energy bound state, and at this point the S-wave scattering length diverges, because you can see this wave function here is basically parallel to the axis here, so it crosses the axis at plus or minus infinity. So this is really the unitarity regime where the binding energy is 0. But then if you make the potential even deeper, you've got enough energy so that the wave function can turn over and you can actually have an energetically bound 2-body state, in which case the particles, the 2 fermions, so spin up, spin down fermion, form a truly bound object, which is a composite boson. So the 2 spin-half particles make a boson. And so we think of this as, in this regime, the atoms are weakly attracted towards each other. In this regime, there's some sort of resonant interaction between the 2 atoms. And here the 2 atoms can form a bound state. So this is kind of like a very gentle 2-body picture of what happens in a Fesch-type resonance. When you go to a many-body situation, however, the picture is a lot more complicated. So now on this weakly attractive side, we can have a kind of BCS regime where you can form large correlated Cooper pairs, and then above the critical temperature you get essentially Fermi liquid type behaviour. On the right-hand side, where we've got bound bosons, then bosonic degrees of freedom start dominating, and you end up with a gas of bosons that can undergo regular Bose-Einstein condensation. And of course, in the middle here is the unitarity regime, which is kind of where the size of the pairs is of the order of the mean interparticle spacing. And this regime is the regime that we're interested in studying, because it's very difficult to make, or it's essentially impossible to make, exact theories to describe the behaviour of the system in this region. So certainly in the BCS limits and the BEC limits, we have well-established theoretical tools that we can use to understand these systems. But here is really where the developments can be made. So this is going to be where we're focusing on this strongly interacting regime. So there's kind of still some debate about whether or not there's a pseudo-gap phase that exists at unitarity. We may hear more about that today, but certainly it's an interesting area for investigation. All right, so with that introduction, I'll now move on to one of the experimental tools that we use at Swinburne that we've developed. And you can think of it as a kind of analogue of neutron scattering experiments in, say, liquid helium or something like that. So the idea is, it's Bragg scattering. So the idea is we have a cloud of trapped atoms that we hold in some sort of optical trap. It's very cold, etc., etc. We've already cooled it down. And then what we do is we fire in 2 laser beams that are oriented at some angle here, 2 theta. And these laser beams intersect at the region of the atoms. And so what happens there is you get an interference pattern, but you can tune the frequency of the 2 laser beams such that they might be slightly different. So we've got here frequency mu plus omega, and here frequency mu. And what the result is that this interference pattern actually moves at a velocity of omega upon k. And so then you can go through fairly simple conservation of energy, conservation of momentum arguments, and work out the Bragg conditions. So for an atom to absorb a photon from this laser beam and undergo stimulated emission into the other laser beam, the atom must acquire or receive 2 momentum recoil kicks. So the change in momentum is just h bar k1 minus k2. And in order to make this a resonant process, what we need is that the energy difference between the two lasers, this h bar omega, should be equal to the change in kinetic energy of the atom. So this is a very, again, a kind of single particle picture of Bragg scattering, but it gives the right feel of what's happening. So when these particles, so what we need is that this change or this difference in the laser energy should match the gain in kinetic energy of the atoms as they scatter a particle. So that allows us to write down the Bragg condition, which is just omega r h bar k squared on 2n, where k is just the wave vector of the interference pattern, so the wave vector of the probe that we're using here. And so what you'll notice about this, this Bragg condition that's kind of useful for us from an experimental point of view is that it depends upon the mass of the particles we're scattering. So if we've got a gas which contains some free fermionic atoms or contains some pairs or molecules, we have now a way to try and separate or to separately address the paired part and the atomic part. And so this was when we realised this, we thought, well, maybe this Bragg spectroscopy is an interesting tool to learn about these strongly interacting Fermi systems. So I should also say that just regular absorption imaging, if we take a picture of the cloud, if it's molecules or atoms, it essentially looks identical. We've got no way to tell them apart just by taking a picture of them the way we normally do. All right, so experimentally what this looks like, so we have our atoms trapped in some sort of optical trap here, so we've got a cloud in the middle. We then flash on these two Bragg laser beams that illuminate the cloud. We do that for a short time, typically 100 microseconds or so. Then immediately after we've done this, we turn off the trap and release the atoms and then take a picture of what they look like. So the way we do imaging in cold atom experiments usually is that we release the cloud from the trap, we fire on a resonant laser pulse, and then we make an image of the shadow that the atom cloud leaves in that resonant laser pulse. And so the sort of pictures we see, if we don't apply the Bragg lasers, we might see something like this, where the cloud just expands isotropically. But if we do apply the Bragg lasers, you can see that we've actually made quite an impact on the cloud. We've kicked some atoms out, and there's also some distortion here to the parent cloud due to collisions between Bragg scattered and unscattered particles. So initially when we saw this, we were worried because we thought this is a bit of a mess, and how can we get quantitative information out of that? But then we remembered some very helpful first-year physics, and that is that any elastic collisions preserve linear momentum. So what we can do, because we know our Bragg pulses transfer momentum along this direction, we can essentially just integrate these images along the vertical direction here, obtain line profiles. From these line profiles, we can determine a centre of mass just by evaluating the first moment. And then we can do this as a function of the frequency difference between the two laser beams. And what this provides then is a direct measure of the linear response function. So provided we use relatively weak probe laser powers, we can directly measure this linear response function. So I should emphasise here that that the majority of our experiments are done with a large K, so this wave vector that we use is quite large, and that means that the atoms that we Bragg scatter come right out of the Fermi surface here. And so in this limit, with low temperature and large momentum, this quantity is essentially a measure of the dynamic structure factor just through the fluctuation dissipation theorem. All right, so that's what we're going to do. We're going to measure the momentum transferred to the cloud as a function of this Bragg frequency, or the frequency difference between the two lasers. And we see plots that look something like this. So this is just a measure of the centre of mass displacement of the cloud as we vary the laser frequencies. And this is done for a range of different interaction strengths. So a range of different magnetic fields. So we use magnetic fields, of course, to do this control of the interaction. But basically, as we look on if we look on the BEC side, or the Bose side of the Feshbach resonance, what we see is that the spectra is dominated by a very large peak at around a frequency of 150 kilohertz. And then as we go across to the BCS side, as we go across the resonance, the spectra look much more like that of an ideal Fermi gas. So basically an ideal Fermi gas is a broader curve centered around something like 300 kilohertz. So the atomic recoil frequency here is just under 300 kilohertz, and so the molecular recoil frequency, or the pair recoil, should be about half that, which is where we see this peak in the response. So this really is a measure of the dynamic structure factor, the density dynamic structure factor for a strongly interacting Fermi gas. And you can see the role of this pairing feature in the response, even at this relatively large momentum. So what I'll draw your attention to now is this black point here. So this is at 835 Gauss, which is very much on the Feshbach resonance. So you can see, so this is where just a purely two-body system would not support a bound state, but in the many-body system you can see there's actually a clear signature of pair scattering at this frequency. So these were quite early measurements that we did. We've since improved things a little bit, and we've tried to study this the response of a unitary Fermi gas a bit more precisely. So last year we made some more precise measurements of this. We improved a number of things in our experiment. And you're actually able to see now that for the unitary Fermi gas, there's actually a very large, very strong response at omega r on 2, which is kind of surprising when you think that the two-body binding energy is actually zero in this case. So there's possibly another temperature scale I should tell you here, and that is the critical temperature for superfluidity in the unitary Fermi gas is actually something like 0.17. So this is well below the superfluid transition here. So that, we'll see later, is actually a key, or this part of the response is a kind of a key signature of superfluidity, or the superfluid transition in this system. So by making this precision measurement of the dynamic structure factor, we're also able to integrate this to get the static structure factor. And the static structure factor turns out to be related to a parameter called Tan's contact parameter. This coefficient out the front, I over NKF, is kind of a dimensionless measure of the contact. And so we've now made a measurement of this contact parameter using this data, which is accurate at the level of a few percent. And this is quite significant now because to date, theoretical predictions, including those from the Strinati group at Camerino, have kind of been at the level of agreement about 10% with each other. So knowing this parameter accurately is important for really pinning down some of the theoretical methods, or validating some of the theoretical methods. And I'm happy to say that actually Giancarlo's group's result is possibly the closest result to our measurement. So that's kind of nice to know. So okay, so now I want to look a little bit more at this pairing peak. So this sharp feature that we see at half the atomic recoil frequency. And what I want to say is, well, can we learn a bit more about it than just seeing what we see? So basically, when we do our Bragg spectroscopy, we do it on a cloud that looks something like this. And what you can see from this cloud is that it's most dense in the middle, and the density gets lower and lower as we move out from the center of the cloud. So we confine our atoms in essentially a harmonic potential. So the density varies with position here in 3 dimensions. But that means, and what we also know is that the cloud is approximately in thermal equilibrium, so the absolute temperature across this whole cloud is essentially fixed. But the important temperature scale is actually T on TF, and the Fermi temperature varies with the density to the 2/3 power. So in a single cloud, when we make a measurement of the response function, what we're doing is essentially integrating over a whole range of different relative temperatures and relative wave vectors as well. So we'd like to try and address this problem and see if we can do a bit better than just measuring these integrated response. And so what we tried was a slightly different approach to the Bragg experiment. So instead of using a very long time of flight so that the scattered atoms move a long way away and we've got a nice big signal to measure, etc., we thought let's try doing Bragg experiments with a very short time of flight. And so we did that, and these are what the two images look like. So this is with omega of 0, so basically no Bragg response. And this is with omega of half the atomic recoil, so we're right on the peak of the response. And you can see there's basically not much difference between the two images. So we're scattering atoms from left to right here, and I'll call this the Z direction. Now that it looks like not much is happening there, but it turns out that if we actually subtract those two images, we can see quite clearly that there has been some displacement of the cloud from left to right. Moreover, if we now look at these sorts of images as we vary the Bragg frequency, you'll see that we get these kind of difference pictures, but if you squint a little bit and turn your head on the side, you might be able to convince yourself that this image is kind of brighter or more intense near the centre than this image at the atomic recoil frequency, where the response is more diffuse and comes from a broader region in the cloud. Okay, so what we can see here is we can actually get information as a function of the position along this z-axis of this response function. So what we did is we performed a Bragg spectrum using this very short time of flight, and then we divided our cloud up into strips like this, so say 6 strips, and we just looked at the response functions for each of these strips. And what you can see is quite clear that there's a very distinct change as we move from the centre of the cloud out to the wings here. So in the centre of the cloud, we've got a much stronger pairing signal. The atomic response is a little bit lower, but then as we go out to the wings here, the atomic response becomes the dominant feature in the spectrum we measure. So we're learning something about the one-dimensional response function, but actually there's still a problem. We're still integrating over the line of sight direction here, and we're integrating over this direction. So we'd still like to do better, and it turns out that we can. And the way we do it is to realise that what we measure here, so essentially this one-dimensional or line response function, we can write that as a density-weighted integral of the homogeneous, or the local response function, so multiplied by the local density, integrated over x and y. And of course we've got the line density out the front here just to normalise it, because we're measuring the centre of mass displacement. Now we can use so because we're using a harmonic trap, we've verified the harmonicity of our trap very carefully. We can actually use the local density approximation, which tells us that the chemical potential at any position in the cloud is just the chemical potential at the centre minus the trapping potential. And so you can rewrite this integral, dx dy, as an integral over d mu, the chemical potential. This is fairly straightforward to show. It was first pointed out in 2007 and then again in 2010 by Jason Chizo. So when we put this into that equation, we get an integral that looks something like this, plus some constants that appear at the front. But then what we can do is we can take the derivative of this. And the nice thing about that is that we know d mu dz very precisely, because we know our trapping potential very precisely. So what that allows us to do then is pull out the values of this function, so the local response times the local density times this derivative of the chemical potential at the two limits of the integration. Okay? The chemical potential goes to minus infinity limit, obviously is 0 because the density goes to 0 at that point. So what we're left with is only the response times the density along the axis of the trap. Okay? So this is all local. So what we're left with is now is just local quantities that exist along the axis of the trapping potential. And I want to emphasise that this is actually a general procedure that can be used for any measurements in a harmonically trapped cloud. And so then you can apply the Gibbs-Duhem equation and simplify things a little bit and get this expression for the local response function, just involving the derivative of the line response times the line density with respect to the line density. Okay. So, all right, so let's see now what our spectra look like. So actually, the first and essentially our only guiding theoretical calculations for these measurements were done, in fact, by Stefano and Roland Combesco and Sandro Stringari in 2006. And they predicted that at unitarity the response should look something like this. But of course in a trapped gas we get something that looks like that, which is not quite different here. So then we thought, well, let's apply our procedure for extracting the local response and see what it looks like. And in fact, it looks qualitatively at least a lot more like the theoretical calculation. So this pairing feature really dominates the response at low temperatures here. We can also do this at multiple different temperatures, and what we see is that as we increase the temperature, so the height of this pairing peak goes down, and then eventually we get something, if we go above, say, 0.2, we get a response that's actually much more rounded and looks like no sharp features anymore. So we thought, well, that looks interesting. Let's just sit at this Bragg frequency and measure it for a whole range of different clouds and see what we see. And in fact, what we see looks like this. So we can see as we lower the temperature down, so this is looking actually at a small range of momenta, so we had to use a large number of different clouds to do this measurement. But what we see is that the response actually increases a bit as we lower the temperature, but then all of a sudden around 0.2, we see kind of a sharp change in the gradient of the response function. And so the way we interpret this, because Bragg spectroscopy is kind of essentially a momentum selective process, what we're measuring here is we're sensitive to the number of pairs with zero momentum. So this increase in the response here is a direct signature of the formation of a pair condensate in the unitary Fermi gas. So this is an in situ signature which previously has not been available in the unitary Fermi gas. It's interesting also to note just how these correlations build up as we lower the temperature. So if we compare with the ideal Fermi gas response, it looks something like that. So it even has the opposite gradient to what we measure. But however, I should emphasise this is not a signature of preformed pairs, it's just an enhancement of pair correlations. So both pair and free atom scattering are taking place at this point. But essentially, this signature here is a clear signature for pair condensation. So I mentioned we can also use this method for measuring other parameters. And so now I want to come back to this contact parameter. So what I showed you before, our measurement of the contact was done on a trapped system, but actually would be more interesting if we could do it or if we could apply this technique to get the contact locally, where we're not relying on any integration or any assumed dependence of the contact in an inhomogeneous gas, which requires some assumed knowledge of the equation state of the gas. And so previous measurements of the homogeneous contact and calculations are shown here. So there's a measurement from the ENS group in Paris. There's some measurements from Debbie Jin's group at Gila. And what they saw was an interesting feature that somewhere near the superfluid transition, it looks like there's a kink in the data. And so I guess Giancarlo recognises his theory here, which actually predicts which predicted a peak in the contact near the superfluid transitions. Other predictions have a discontinuity. Others show a kind of sudden decrease in the contact. So we're kind of interested to look at this region. Now, unfortunately, our data at this stage looks like this. So we really can't say too much about this, what we really believe is happening, but it's still a work in progress. And the issue here is that we have to differentiate experimental data, which is inherently a noisy and dangerous process for any experimentalist. But nonetheless, we're trying and we're working on it. But still, we still see something that's roughly in the ballpark, but just our error bars are still quite large from this process. So this is an ongoing work, and if you see me pattering away on MATLAB, then I'm probably working on this data as we speak while I'm here. All right, so the final thing I'll talk about today is some new experiments that we have underway at Swinburne on studying two-dimensional Fermi gases. And so in two dimensions, obviously, it's quite different to 3 dimensions. The scattering physics is different. So for any arbitrarily weak attractive interaction, you always have a bound state. And this has major consequences for the phase diagram and things. So we'd like to also address this with our experiments. So the way we make two-dimensional Fermi gases at Swinburne is we basically confine atoms between two Blue-detuned laser light sheets. So we make a TEM01 mode laser beam, and that provides essentially two parallel sheets that we squash our atoms between. And then in the two radial directions, so that provides tight confinement in this Z direction. And the two radial directions are actually confined magnetically by the fact that when we use the large magnetic fields that we need to reach the Feshbach resonance, there's some residual curvature in those fields, which means the atoms tend to seek out the centre. So the nice feature of this is that this potential is extremely harmonic and we can characterise it very precisely. And in this direction, we're really confining atoms, or our aim is to confine atoms to the transverse ground state. And in that way, this is kind of a 2D system, or at least a quasi-2D system. So when we do that, experimentally our laser trap looks something like this. So this is a kind of head-on view of the two laser beams that we use for trapping. And when we take pictures of the atom cloud loaded in this trap, so from the top it looks like this, so it's nice and round and flat, but from the side you can really see how flat it is. And of course this is actually, we're actually diffraction limited in this image, so the width of the cloud you see here is because the diffraction limit of the optics essentially, or the fact that the cloud is so long. So put it in perspective, this is something like 300 microns across this cloud. And in this tight direction in the trap, it's less than a micron. It's something like 500 nanometers. So very, very asymmetric trap. And I should acknowledge there's a number of other groups working on 2D Fermi gases as well now, but they're mostly using optical lattices. So achieving 2D, what we mean by 2D is to say that in the radial direction we'll have many harmonic oscillator states that we can fill, but in the transverse direction we only have one. So we need to choose the system such that the Fermi energy lies well below this first transverse excitation. And so what that means is that we need to count the number of quantum states that we have available in here to see how many atoms we can put in our trap before eventually we must start occupying this transverse state. And so what that means is that we want the total energy to be less than the energy of the lowest lying state with one quanta in the transverse direction. And this turns out to be just proportional to the square of the aspect ratio of the trap. So omega Z is our tight confinement frequency and omega R is our weak frequency. So in our trap we typically have something like 5.7 kilohertz in the tight direction and roughly 25 hertz in the weak direction. And this means we get a maximum atom number of something like 50,000. And so that's good, and we can verify that. I should, before I do that, I'll show you some early measurements that we did in a trap with a much lower aspect ratio. Remember I said the critical atom number goes with the square of this. In fact, there's an additional factor of 2 because here we're looking at only the atom numbers in a single one of the spin states. And so we did some measurements of this previously where we looked at the evolution of the cloud size as a function of the atom number. And so this provides a nice signature when you're in the two-dimensional regime or when you leave it. So basically in 2 dimensions, because there's only 4 phase space degrees of freedom for your atoms to fill, the cloud width grows with n to the 1/4 power. Whereas in 3 dimensions, you get the P and the Z in the Z direction. And so you've got 6 dimensions to fill, and so then the cloud size should scale with n to the 1/6. So what you should see then is some sort of elbow in the scaling of the cloud width as you increase the atom number. And indeed, this was something we did in 2011, and is what we see here, but this is with a very weak trap. We can also look at the width in the transverse direction after release, so to try and measure the release energy, and we see that it starts off fairly flat and then increases as we put more and more atoms in, indicating that we're filling higher and higher transverse oscillator states. So the other thing we can do with this data, once we have these 2 bits of information, is take the ratio of the 2, which is essentially a measure of the aspect ratio of the trap, and what we see is how it evolves as a function of the atom number. So you can see that for very low atom numbers, the aspect ratio changes quite quickly. Then it kind of plateaus a bit, then it seems to have a jump and plateaus again. Of course, in 3 dimensions, this would just be completely a flat line. So by taking the derivative of this data, we got something that looks like this, which is basically consistent with the theoretical curve. So the solid line is for a weakly interacting Fermi gas, and these arrows indicate when new transverse states become energetically accessible. So we can see here probably the filling of the first shell, maybe even when we start to occupy the second transverse excited state in this trap. With our new trap, however, we can do much better than that. And in fact, with our new trap, we can measure the cloud size versus atom number. And here, thanks. Here what we see is quite different, that the atom number grows fairly linearly, or well, on a log, so this is a log-log plot, so it's got a gradient here of 0.22. And then once we get above this region here, the gradient is something like 0.14. So this is a signature for the transition from 2D to quasi-2D. This is not really 3D, of course, because we still have the discrete nature of the transverse states is still very important here. So this is still in the quasi-2D region. Okay, so this, and from the point here where these intersect, we're close to 50,000, which is about where we'd expect to be. The total atom number is close to 50,000. All right, so now armed with this knowledge, we can now prepare reasonably large atom clouds, so say with 40,000 atoms, and know that we're predominantly in the transverse ground state, at least at low temperature. So what we can do then is just measure the density profile as a function of, say, the interaction strength, which we now quantify by the 2D binding energy. And you can see that in a single shot, we can actually get quite good images. And so what this is now, because this is a two-dimensional system and we're imaging it from the top, we're directly imaging the density profile here. Whereas in a 3D Fermi gas, when you take any absorption image, you're always integrating over one direction. But this is actually directly providing us the two-dimensional density now. And so we can take a picture like this. We can then integrate it, or we can average it elliptically around here, so we know the lines of equipotential. So we can just and then, of course, symmetric around the centre of the trap, so we can just average the density around that. And this gives us a very low noise determination, or low noise plot of the density versus the potential. So with this, we can now ask the question, well, what's the equation of state for this system? And so, as was shown recently by the MIT group, for a three-dimensional Fermi gas, if you have accurate plots of the density versus potential, you can construct the equation of state. So in 2 dimensions, the equations of state for the pressure, density, and compressibility are all linked by this universal function, f of p, which is a function of beta mu, so this is the chemical potential divided by the temperature, and the binding energy, so EB is the two-body binding energy divided by the kBt. And so this function, or the derivative of this function, connects all of these three properties. And so following the approach for the 3D Fermi gas, and also that's now been used...
So the derivative with respect to what argument? Because I see 2 arguments and then the derivative is taken.
That's a good question. So beta mu is actually the derivative. Yeah, okay. Sorry. Yeah. So beta EB is fixed for a given cloud. So it depends which way. I mean, so in our experiments, it's mu that varies with position, and EB times beta, that's a constant. So it's only this term that we have to differentiate. But yeah, in general, it's actually both. You have to be careful. Thanks for pointing that out. Yeah. And so this has also been studied. This method has now been adapted for a 2D Bose gas at ENS in Paris. And so we have some preliminary data on this. So what we're doing here is plotting the dimensionless compressibility versus the dimensionless pressure. So kappa naught is just the compressibility for an ideal Fermi gas at T equals 0 with an equivalent density. And similarly for P naught, it's just the pressure for an ideal Fermi gas at equivalent density. And so we can make plots like this, which actually is a measure of the equation of state. However, it's not quite meaningful yet because we don't have a precise thermometer. And so this is something that we're working on now. And what we're using for our thermometry is actually comparing with theoretical calculations in limits where they're known. So it's known that at high temperature you can use a virial expansion to obtain the equation of state. And so out in the wings of our clouds, the kind of temperatures that we have there should be well described by this virial expansion. But unfortunately, the preliminary work we've done, the data's still kind of noisy to get really meaningful information, but this is what we're working on. We've also made some comparisons with some quantum Monte Carlo calculations, again from Stefano Giorgini and collaborators in Trento. And at this stage, our data sits a little bit above the zero temperature results, which I don't really understand, doesn't really make sense. But anyway, this is still a work in progress as well. But this is where we're going with this experiment. So I'll finish off there and just say that I've tried to give you a flavour of what we can learn with Bragg spectroscopy and what's some of the interesting things we can do with two-dimensional Fermi gases. So the next step is to look with, is to really get some accurate thermometry for the two-dimensional system, and also we're developing a low momentum Bragg laser so that we can probe the collective response and collective properties of the superfluid. And so with that, I'll thank my team, in particular Marcus Lingham, who's responsible for a lot of the Bragg work, and Christian Fennick, who's really driving the 2D work, and of course our theoretical collaborators, Wei Hu and Xiaoji Lu. So thank you very much for your attention today.
Thank you very much, and immediate question, please.
Yeah. Do you have any preliminary results about coherent behavior, some oscillations of DC as calculated by the group of Vale?
No, not yet. So are you talking specifically about the 2D case, or?
I mean, in positive regime, when you have increase of the number of perpendicular levels, you have oscillations of DC.
So the real difficulty is that we're pretty sure that we're not at a temperature yet that's at the critical, that we haven't reached the critical temperature in 2D, because, so in true 2D, the critical temperature is something like 0.1 of the Fermi temperature. And it's actually, with the system we've got, it's hard to reach that. But that's a work in progress. So yeah, we're definitely pushing towards those lower temperatures.
But do you feel that it's reachable?
I think it is reachable, yeah. I think it is reachable. It may be tricky, but I mean, particularly I think as you go more and more quasi 2D, then the critical temperatures become higher. I guess eventually they approach the 3D limit, where we know we can easily reach the superfluid transition temperature. But really to get to a BKT transition in this system is going to be quite challenging.
Yeah.
So.
Yes, related to this question, but you show already that you have some sort of resonance in, when you are in the quasi 2D.
Yep.
So one of these new level enters.
Yep.
So still this is some evidence that your system, for whatever temperature you are, feels the fact that you have.
Absolutely, that's right. But there's no superfluid or anything.
No, of course not.
But you're absolutely right.
It's the density of the states.
Absolutely, yeah. We can see identify each
because
state.
my question was related to that. It's just, but why the peaks are so broad? You show it. You talk that the peaks when a new state enters are quite broad, just because of the temperature.
So no, it's not. So even at zero temperature, you would expect them to be broad. They kind of show this shell structure, but it's basically, I mean, when you start occupying the first transverse excited state, you still have you're still occupying states. You're still also filling the lower transverse level as well, but you're just filling it with higher radial shells, if you like. Yeah. So you're doing both things simultaneously. So you start populating the transverse one, and you see a change, but it's not a.
So it's not related to any loss or something like that.
No.
So just the fact that you just.
There's no loss. No.
Populate.
It's just filling up higher. Yeah. Just counting states essentially.
Yeah. Okay, next question over there.
You used the pure harmonic oscillator value for analyzing your response function.
Yep.
That is changed because of the Hartley field. It's not purely harmonic. How much effect is your...
So I mean, we're really only relying on the local density approximation. That's the only kind of restriction that comes
the
here.
real potential is not completely harmonic because of the Hartley field.
Well, it's just, I mean, it's harmonic to as good as we can measure.
Oh.
And so I think I think what you're asking doesn't come into it, but maybe we should discuss it later. I mean, it's really, just that we can write down mu is equal to mu naught minus v of r, so long as that's valid, and so long as that's valid for the response function we're measuring, then it's okay. Yeah.
Okay.
I think it covers
One
it.
more quick question.
Is it possible to measure the response function at different momenta?
Yes, yes. In fact, that's the last point that we're doing.
At low Q and also high Q is interesting. The volume moves.
Absolutely, yeah. I mean, low Q experimentally is much more challenging because the signals we have are necessarily small, because the signal we measure is proportional to Q. But we've spent a lot of time improving the high Q signal, so now we're confident to try it at low Q, so yes. So this setup that I mentioned we're talking about, we're roughly around 0.4 of the Fermi wave vector with that. And so I think that's really, we'll be able to look at the collective behaviours.
Okay, so let's thank Professor Vale again.